Okay, let me welcome you to another CLSP seminar. It's my pleasure to introduce Geoffrey Zweig. Geoffrey Zweig got his PhD from Berkeley. I don't know what year, but it's in 1998. And he's now manager of advanced large vocabulary speech recognition systems at IBM.
Thank you. So I understand that there's a variety of people in the audience. Some people, hardcore speech recognition type people, and also people who are just sort of more generally interested in computer science-y type things. And so when I went to think about what I was going to talk about today, I wanted to pick something that covers speech recognition and comes from speech recognition, but maybe has a little bit of a more general flavor to it. And so I thought back on what I had done over the past few years, and I decided to talk about this particular problem, which has to do with factoring decoding graphs, so that you get a small representation of the search space that you use in speech recognition decoders. I think it's sort of an interesting problem that combines speech recognition with some interesting computer science algorithms. So the outline of the talk is I'll talk a little bit about the ASR background, and I hope it's not too elementary. I thought there might be some people who would appreciate some background. Static and decoding graph strategies, static and dynamic decoding graph strategy, static and dynamic strategies for doing speech recognition decoding to find the likeliest word sequence. The problems that we run into when we start having long span acoustic context, where the way that you pronounce something depends on what you've said, maybe in the previous word, and also what you're coming up on saying in the following word. And then a way of getting around this problem with long span acoustic context that has to do with factoring the decoding graph. And this is sort of a fundamental problem in trading non-determinism in the decoding graph for a reduction in size. And it turns out to be an NP-complete optimization problem in order to find the smallest acceptable graph. I'll talk about some heuristics for getting around that problem, and then present some experimental results and talk a little bit about a couple of related problems. Okay, so just the fundamental equations, just to set the background of this whole thing. What are we after? We're after the likeliest sequence of words given some sequence of feature vectors. And we apply Bayes' rule, and we say, well, we're going to break it down into the probability of the word sequence and then the probability of the feature vectors given the word sequence. But then we say, well, it's too hard to go directly from the words to the feature vectors. We need some kind of an intermediate representation in there. And in particular, we know that words are broken down into sort of more atomic units of phones. And so we're gonna actually think about this in terms of a mapping first from words to phones, and then from phones to the acoustic vectors. And that's still even not quite enough, because there are all these co-articulatory effects where when you talk, what you say, how you pronounce a particular phone, is affected by the phones that you're saying before it and what you're thinking of saying next, the anticipatory effects. And so we're going to add an extra concept in here, which is the notion of an acoustic state, which you can roughly think of as how your mouth is configured, what you're doing when you're talking, how the pieces are moving. And we'll break the whole thing down into a prior on word sequences, and then think about the probability of a phone sequence given the word sequences, which you can get by looking at dictionaries, the probability of a state sequence given the phone sequence, and then the probability of the feature vectors given the state sequence that you think the person is going through. And that first one is the language model. The second one is the pronunciation model. The probability of a state sequence given a phone sequence is a co-articulation or context model, which is typically modeled with decision tree. And then finally, we have the feature generation model that gives you the likelihood of a feature vector given that you're in some particular state. Okay, so what are the components that, how do we represent these components? The language model you can think of as basically just an enumeration of the probability of a word given some predecessor words. We typically use n-gram language models. So if you've seen cat in the, you might be able to go and look up somewhere the probability of hat, the phrase cat in the hat, and get that. Now, you can't represent or you can't record all possible n-grams of things that people would say. There's too many of these n-grams. And so we're going to use a back-off language model. So if you haven't seen a particular word in the context of some predecessor words, you can go and look up, instead of, say, the 3 previous words, just the 2 previous words. So somewhere we'd have recorded the probability of cat given in, a hat given in the, and then continue to back off. The pronunciation model you can get by looking at a dictionary, and just seeing that, okay, people say tomato and people say tomato, and maybe you have you go off and you collect some statistics and you have the relative probabilities of those. The co-articulation model is typically encoded as a decision tree where you take a sequence of phones and you want to know what the state sequence is. The decision tree asks questions about phones. So you take a particular phone, you take a context window of phones around it, like maybe the 2 or 3 preceding phones and the 2 or 3 following phones. And then you send it down a decision tree that asks questions like, is the phone to the left of the center phone a nasal? Yes, okay, I'm going to go over here. Is the phone 2 phones to the right a plosive? No, I'm going to go over here. And you keep asking these questions, and eventually you get to a leaf of the decision tree, and that's the acoustic state that you use to model that phone in the context of the surrounding phones. Associated with each of those acoustic states is a Gaussian or a mixture of Gaussians that gives you the likelihood of a feature vector given that you're in that state. Okay, so those are the components, and basically what this talk is revolving around is the problem of combining those components to figure out what was the most likely word sequence that somebody said. The one way of doing that is to sort of combine them on the fly as necessary in a dynamic way so that the portions of the search space, the word sequences that you consider, are only those word sequences that have some reasonable probability given the acoustics that you're looking at. So for example, maybe you've decoded so far the words a hot. You might then apply the language model and say, okay, well, a hot meal, that's got a good probability. A hot deal, that's got a good probability. I'm going to consider the words meal and deal as successor words. And so you add them in there. Then you could apply the pronunciation model that says, okay, meal is pronounced with these phones, meal, and deal is pronounced with these phones. So really what I'm considering is a couple of paths that look like this. And then you could apply the co-articulation model and take the phones of meal and send them down the decision tree and get a state sequence. And the same thing for deal. And so now you're saying, okay, I think I've got a hot followed by either Q1, Q2, or Q3, or a hot followed by Q4, Q2, Q7, whatever the decision tree tells you. Apply the mixture of Gaussians or the feature generation model, and then discover that, hey, this path over here actually doesn't match the acoustics at all, so I'm going to kill it off. And I think that one of the paths that I should consider is something that's a hot deal. And then you go back to the beginning, look up in the language model, and keep going. Now I've sort of simplified the process, and if you actually implement a dynamic decoder, you do things in a little bit more sophisticated of a way. But this is just to give you a flavor of how you can dynamically combine the components of the recognizer to do the search. There's a different way of doing it, which is to try to statically represent all the possible word sequences and all the possible state sequences that somebody could utter in the language. So this is a very different way. Here you're saying, look, I want to write down in advance every possible state sequence that somebody might ever utter, and I want to say what the probability of any one of those state sequences is, and I want to store the thing on disk. So just to give a simple example, if you've got a 3-word vocabulary with hat, bat, and cat, assuming that the way that those words are realized doesn't depend at all on the preceding or the following words, you could say, well, hat consists of context-dependent state 7, followed by 4, followed by 8, and then I can loop around and maybe decode bat, which has these states, and loop around and do hat again, and so forth. So we've just represented that 3-word language. Okay, well that's a unigram thing. There's no real language modeling going on there, but it's pretty straightforward to represent higher order language models in this same basic framework. So for example, if you have an n-gram language model, and one of the word histories that you know about is the dog ran, you put a history state in there for the dog ran. Maybe you've got some specific probabilities for the dog ran fast, and you'd have the states of fast. The dog ran home, and you'd have the states of home. And then a back-off arc for words where you haven't seen the dog ran followed by that word, but you have seen dog ran. So maybe you've seen dog ran quickly as in a dog ran quickly. Back off some more so that you just have one word of history, and finally back off to the unigram history state where you have no history at all. So in principle you can just write down everything in your language model and compile it down to the state level here, and then do decoding with that kind of graph. And that's actually the strategy that we've adopted, and that the problem of this that comes up in this talk occurs in. So basically, using a fully flattened HMM representation is good, because once you've got a fully flattened HMM state representation at the state level, you can search it with extremely simple dynamic programming recursions of Viterbi algorithm. You can apply all kinds of optimizations to that representation of the search space at compile time when you first write down the search space to try to shrink it and make it efficient to search. For example, you can determinize it. As you saw in the previous slide, using a co-articulation model that doesn't look at all at the surrounding words is very easy, because for each word you can just write down the phones, apply the decision tree, get the state sequence that you think you have, and basically do a fancy search and replace on the language model where you replace each occurrence of a word with the state sequence. But it turns out that when you have long span acoustic context that crosses word boundaries, once you're willing to cross word boundaries, the whole ball game changes, because you have to consider how is something realized in the context of the previous and possibly the following word. The most straightforward way of doing this was developed at AT&T a few years ago, and that involves, if you're keeping track of context of n phones, it involves having states that represent n-1 phones of context, and then arcs between all those states, making a transducer that represents context by having states that represent n-1 phones of context, and then arcs, and then transducing a context-independent graph into a context-dependent graph using that transducer. But the problem is that if you have a lot of phones, when you do that, the number of arcs is p to the n, where p is the number of phones in your vocabulary, and n is the size of the context window that you're using. And that can be very large if you use a long span acoustic context. And in particular, the kind of acoustic context that we're using in IBM products is a full word of left acoustic context. So the realization of a phone X depends on all the phones in the current word that you find that phone in, plus all the phones in the previous word, Okay, there's a limit of 5 phones on either side, but still that makes 11 phones total. And if you've got like 40 phones, and well, 40 to the 11th is huge. And so the key thing that I'm going to talk about here is how do you deal with that kind of long span acoustic context. I'm going to talk about it in the context of using just a unigram language model, because all the qualitative issues come up in the unigram case, and then you can basically, yeah, there's no new qualitative issues with the higher order n-gram, so we don't need to worry about it. So here's an example of what goes on. It's the same hat, bat, cat example. All of a sudden now, instead of having one way of saying hat, you have 3 ways of saying hat. Okay, if you say hat, hat, you get one thing. If you say bat, hat, it comes out a different way. And if you say cat, hat, it comes out yet a different way. And so instead of having, just one sequence for each word, we now have as many sequences for a word as there are possible predecessor words. So the number of variants in here is all of a sudden square in the vocabulary size. These states over here just mean that you finished a word. So this means, okay, I finished decoding the word hat here, and then I can jump off and go to some hat variant, or I can jump off and go to some bat variant, or I can jump off and go to some cat variant. So the first problem is that since each word can potentially be realized in as many ways as there are other words in the vocabulary, the number of potential variants of words that you have, actual state sequences for words, is square in the vocabulary size. And even if you have a relatively small vocabulary size, like 20,000 word vocabulary, you're looking at something like 400 million variants, and that's a huge graph. It's hard or impossible to just write it down. Fortunately, it turns out things aren't quite that bad in reality. And if you take a standard decision tree, so something that has maybe 10,000 context-dependent states, a 20,000 word vocabulary, and run every word down the decision tree in the context of all the possible predecessor words, you end up with only something like 600,000 variants. And so just writing down the variants isn't so hard. Maybe you've got a couple of different variants of the first word, a few variants of the second word, a few more variants of the third word, and you can just enumerate it out. But that doesn't get us all the way out of the woods, and this is a key problem here.
Sorry, what was your point on the previous slide that there isn't really a separate pronunciation of hat for every preceding word?
Right.
There's only 3 or 4 total.
Of each.
Yeah.
Right. So there aren't too many variants. But here's the big problem. There's still a lot of arcs, because when you finish one word, okay, you're licensed to use one and exactly one variant of every other word. So if you finish this word, maybe you have to use the first variant of this word, hat. If you finish hat, maybe you have to use the second variant of bat. And if you finish hat, maybe you have to use the third variant of cat. So since each word licenses exactly one variant of every other word, the number of arcs that you're looking at there is still square in the vocabulary size. Okay, so we don't have too many lines in this graph, but there's a whole lot of arcs that are connecting the lines. And another way of looking at that is basically as a bipartite graph, which is where the bipartite graph comes in, where you've got words on one side over here, and variants of words or acoustic realizations of words over here on the other side, and connections from the words to the variants that they license. And I've made this a simple one where this word only has one realization, no matter what the preceding word is. This one over here also only has one, no matter what the preceding word is. This one only has one, but down here we've got 3. And just to convince you that there's no funny business going on, if you go back and look at this graph, these are the word arcs here. This means that you've finished the word hat. This means that you've finished the word bat. This means that you finished the word cat. These are the variant arcs over here. So these are the nodes on the left-hand side of the graph. these are the nodes on the right-hand side of the graph, and these are the arcs that are in the middle of this graph over here.
Why is it that each word license is only one variety of the following word?
Because if you take the following word, get the phone sequence, put the phones of the preceding word into the context window, and send it down the decision tree, you get exactly one answer. The decision tree just maps an occurrence of a word in a preceding history to one particular set of acoustic states.
So we're going to stick with left context only, or are you going to surprise us?
We're going to stick with left context.
Okay.
The same problem arises if you're using a word of right context, but it's sort of more of the same, and so I'm not going to go into it.
So this could be applied to left and right context?
It can be applied to either left or right, but if you've got both left and right at the same time, then you've got to do something fancier.
Okay, so you can condition the pronunciation of the end of the word on the following word.
I'm sorry?
You can change the pronunciation of the end of a word based on the following word. How you would run it together.
You can't do both left and right at the same time.
Okay.
But if you wanted only right, you could get away with only right. Okay, so the basic key here is to try to factor the connectivity. We've got this graph here that's a big mess, and over here here's a nice graph that's it looks a lot less messy, and it's been factored. What's happened is we've introduced some extra states. So we're actually increasing the number of states in the graph. But the number of arcs that's in the graph is much fewer. And if you check carefully, you can actually verify that if you could get from here, from point A to point B in the left-hand graph, you can still get from point A to point B in the right-hand graph. And there are actually no places, you can't get from point A to point B in the right-hand graph unless you could also do it in the left-hand graph. There are no spurious connections that are added. So it's essentially like what airlines do, where instead of having flights from every city to every other possible city, they introduce hubs, and then you go to a hub and you fly out of the hub. Suppose we had a method for factoring the graphs so that we could get a sparse representation. Then we could take that factored representation and plug it into the graph that you saw before to come up with a final connectivity that looks like this, where those extra new states that we introduced in the middle of that bipartite graph, those extra states are put down here, and then you can get from the left-hand side of the bipartite graph over to one of the middle states, and then back over to the right-hand side of the graph by doing 2 hops. So that's basically where we're going, is we're going to try to take the graph and deal with the graph structure, deal with the arc structure by introducing extra arcs, and then having a graph structure that looks like this.
And the extra states effectively describe equivalence classes of words.
Yes. Okay, so what have we done? We've taken a graph that looks like this, and we've actually partitioned the edges into bicliques. So a biclique is a subgraph of the bipartite graph where all the nodes on the left-hand side are connected to all the nodes on the right-hand side of that subgraph. So over here in red, you see one biclique. This, and this are connected to this, and this. Every node over here is connected to every one of those, and that's in red. Another biclique is in green here, where these 3 are all connected to this one. Every one of these is connected to every one of these, but there's only one of these on the right. And then here's another one, and then here's another one. So we've taken this whole set of edges and partitioned it like this into a set of bicliques. And then we've replaced the bicliques, each biclique that occurs in the graph, with a tree, where we've introduced a root in the tree the nodes on the left go into the root, and then the root has arcs to the nodes on the right. And that's the basic factoring process, is find the bicliques in the graph, and then replace those bicliques by trees, and you reduce the number of arcs. Yes?
Why do you need partition? Could you have used the same agent more than one biclique?
Good question. And the answer is yes. You certainly could, and actually, in a little bit later in the talk, I'll ask that very same question myself. But it has to do with proofs. Okay, and when we do this partitioning, there's something that we want to minimize. We want to minimize the number of edges in the final graph, and if you think about it, that's equal to the sum of the number of vertices in each biclique. So like if you look at this the green biclique there, how many vertices are involved in it? 1, 2, 3, 4 vertices are involved in the green biclique. And the way to see that it's equal, that the number of edges is equal to the number of nodes, is that each node on the left-hand side has one edge that goes to the center state, and then each node on the right-hand side has one edge that comes out of the center state. So it's, so the number of nodes tells you how many edges you're going to have to put in there. Well, guess what? It turns out that that's an NP-complete optimization problem. Finding the partitioning of the edges in the graph to minimize the number of vertices involved in the bicliques is NP-complete. That was proved by Feder and Matwani in 1991. And I'll just briefly go over it. The statement is the minimum order partition of a bipartite graph into bicliques is NP-complete. We talked about what a biclique is. The order of a biclique is this count of the number of vertices that are involved in it. And then if you have a partition, the order of the partition is the sum of the orders of the constituent bicliques in the partition. So here's an example. There's a little graph there. There's one biclique, and for historical reasons, they're described by Ks. This is a K22, meaning it's got 2 nodes on one side and 2 nodes on the other side. The order is 4. There's 4 vertices involved in it, and it covers 4 edges. Here's a K13 that's also order 4. It's got 4 vertices, but only covers 3 edges. Okay, so what Feder and Matwani showed was that this is NP-complete, and the reason is that you can take a 3-sat instance, and you can transform it into a bipartite graph that contains only K22s and K1Qs. So those sort of star things where there's only one vertex on one side and several on the other. That sat instance actually has a property that it's, or the graph has the property that the sat instance is satisfiable if and only if the graph's edges can be partitioned into K22s only. Partitioning into K22s also happens to minimize the order of the partition. And that's because, well, one way to see it is K22s remove 4 edges at cost 4. They hit 4 edges, and the cost is 4. That's, you pay 1 for each edge. K1Qs remove Q edges at cost Q plus 1. Remember, we saw that example with 3. There was 3 edges, but there's 4 vertices, 1, 2, 3, 4. So the amount that you pay per edge is more than 1. So now there's a fixed number of edges that you have to hit in the graph, and the minimum cost is going to be if you can cover each edge exactly once using a structure that incurs only a charge of 1 per edge. And that means precisely partitioning it into K22s. So if you ask for the minimum order partition and the order of the partition ends up equaling the number of edges, it's been partitioned into K22s and K22s only, and the sat instance is satisfiable, otherwise it's not. And so that's basically how they They showed that it's NP complete. Okay, so what do you do when you have an NP complete optimization problem? You say it's time for heuristics. And we developed two different heuristics for this that I'm going to describe. The Cartesian intersection algorithm, something I'll call the Cartesian intersection algorithm, and another one that I call the basis set algorithm. The key idea of these things is to manipulate sets of predecessor words and the allowed successors. This gets to your equivalence classes on predecessor words comment. So here's some notation. I'm going to refer to Pij as the jth context-dependent variant of word j. So remember, hat had a few different variants, and so P hat j would be the jth variant of the word hat.
The ith word is an I and a j.
Oh, I'm sorry, that should be I. That's a typo, that should be I right there. A history pair looks like this, and the way to read it is, here's a set of words, word A, word B, word X. Here's a set of variants, and having this word as a predecessor word licenses any of these variants. Any word over here as a predecessor licenses any of these variants. The connectivity pattern of individual words can be represented by a collection of these history pairs. So here's a word, word I, and what this means is, look, if it's preceded by word A, word B, or word X, use variant number 1 or variant A. Also for word I, here's a second variant, variant 2 or variant B. If it's preceded by words C, G, T, or Y, you better use this variant over here. And so the connectivity pattern of an individual word can be just represented.
The purple A and the green A have nothing to do with each other, right?
The purple A, they have nothing to do with each other. It would have been better if I had made these 1 and 2.
Okay. Thanks.
Yeah, and so this guy here, from time to time, I may refer to as a word set, and this one over here as a variant set. And another way of thinking about this word set is as the left set of this particular variant, the set of words on the left that license this variant. So what's the basic idea of the Cartesian intersection heuristic? It's to maintain a collection of licensed history pairs and then repeatedly add the constraints that are imposed by a single word. And the key observation here is that if you have two word sets and you intersect them, you find what they have in common, that intersected set is going to license the union of the variants that were licensed previously by each of them individually. And so here's an example of that. Suppose you've got this set of currently licensed history pairs. So these words are good for these variants. These words are good for these variants. And then you want to add a new word. And here are the constraints of this new word, word I. You take the Cartesian intersection of everything over here with everything over here. So let me just give the answer. The intersection of this word set with this word set, they have words A and B in common. So you see A and B over here. And the union of this variant set with this variant set is this set over here. And that makes sense, right? If A was okay to use with this, and A was okay to use with this, and A is okay to use with this, we're saying the same thing over here. A is okay to use with any of them. So the intersection of this with this, they don't have anything in common. The intersection of this constraint with this history pair, they have C in common, so we get a C over there. So here C licensed PMA, PYB, and here C licensed PIB. So C certainly licenses PMA, PYB, and PIB. The intersection of this with this is just D. So word D licenses a union of these two variant sets, which we have over here. And then we take this one over here. The intersection of this with this is nothing. And the intersection of this with this is EFG. So over here we have EFG licensing the union of those variants over there. Maybe I should just wait a minute here. Any comments on that one? Because if you think about it, it's sort of interesting what's happening there. But all the words, you never lose words.
So all the representation represented on the left,
Yes.
that can be found somewhere over on the right.
Right, exactly. Everything over here can be found over here, but it's sort of been shattered by these constraints. So it may have been broken up into 2 or more lines over here on the right, because you've got to satisfy these constraints also.
So in general, the sets on the left, they're a partition of your vocabulary.
Exactly.
And they're different partitions. And what is on the right is a refinement of both partitions.
Right.
But it's sort of a minimal refinement.
Right, exactly.
Okay.
And
So it's a finer partition which can be coarsened to either this or that.
right,
And then for each finer cell, you're writing down exactly what's permitted. And what is permitted by the first and the second, you take the union because, okay.
right, precisely. Another property is that every word is represented exactly once somewhere on the left over here. And every word is represented exactly once somewhere on the left over here. And when you're done, every word is represented somewhere on the left over here.
So you'd start, for example, for each variant, looking at exactly which vocabulary words it is used with.
Right.
And then this way you'd get the initial partitions and then you keep...
Well, okay, so here
how do you start? Yeah.
so here it is. So here's how you start. You start by putting all the words over on the left-hand side, licensing nothing. And then you repeatedly incorporate the constraints of the individual words. And you can enumerate those constraints in an online fashion if you want. There's some truth in advertising, which I'm going to skip because it's just fine print. So here's an example. Here's that same example that we saw. I got rid of the W sub thing because it was too much to type. So the words are just, there's word A, there's word B, there's word C. And this is variant number 1 of word A, variant number 1 of word B. Here are the constraints. It only gets interesting sort of down here where word E has 3 different variants. The first variant is licensed by words A, B, C. The second variant is licensed by word D. The third variant is licensed by word E. We initialize the algorithm with all the words on the left and no variants on the right. We process the first thing. So we intersect this with this, which is everything, and we add this over on the right. Then we incorporate the constraints of this by intersecting this with this and adding the one on the left, so we get that. We process this set of constraints, intersect this with this and get that, and union this with that to get that. Do the same thing for D over here, and we just add variant 1 of D over here. And now it gets interesting because we're going to take this, we're going to intersect it with this and add this. We're going to intersect this with this, and we're going to intersect that with that. And that gives us this. So here we have A, B, C, D, E. Intersect it with A, B, C, and you get A, B, C. Add this to that, and you get that. Intersect this with that, and it's D by itself. And then we add variant 2 of word E to this set of variants to get that. And that's the answer. And if you represent it in a graph, what we just came up with is this partition right here, or this factorization right here. And we ended up with 20 arcs. The picture that I showed you previously had only 17 arcs, but that's what you get when you do heuristics. You're not guaranteed, always to find the best answer, but we did make some progress. And here's the thing in its full notational glory. Okay, so now the question of partitions versus covers that you had. So the Cartesian intersection heuristic is guaranteed to produce a partition. It's not obvious, from the description of the algorithm, but if you think about it, it turns out that there's no way that you can ever end up with 2 different paths between a word and a variant. But, you know, covers can reduce the number of edges more than partitions maybe. So what about a heuristic that makes covers? And just to illustrate this, here's a graph, bipartite graph. Here's a partition of the edges in that graph, and I think it's the best partition that you can do. And that's got order 9. 1, 2, 3, 4 for the red clique. 1, 2, 3, so that we're up to 7 when you add in the blue clique here, the K12. And then here's a K11 that adds 2 more, and that brings us up to 9. Here's a cover of that same graph in terms of cliques. Basically, what we're going to do is we're going to say, look, here's a K22 up here, and here's a K22 down there. And if you look at the order of that thing, it's 1, 2, 3, 4 plus 1, 2, 3, 4. That makes 8. So that's better. So by getting a cover, we're better. And the difference is we're hitting this edge twice. So what does that mean in terms of the final answer? We're going to end up with a graph that looks like this, where all of a sudden from here to here, there's 2 different ways of getting from here to here. You can either go up and down, or you can start over here, and from this clique, you can go down over to here and up over to here. We haven't introduced any false connections, but there's some redundant connections in there. Do the redundant connections matter? No, because if we do Viterbi, it's going to pick just one of those redundant connections, and we're going to get the same answer as if the redundant connections weren't there. So it's fine if we add them. Well, guess what? Decomposition into a minimum order edge covering by cliques is also NP complete. And an easy way of seeing that is that, look, a partition is actually just a special case of a cover where you hit the edges, each edge only once instead of possibly multiple times. If we go and we take this SAT instance and go off and make our graph that's got only K22s and K1Qs, the graph that we make is still going to have only K22s and K1Qs. The minimum is still going to result from covering each edge only once as a K22 if it's possible. And what that means is that the minimum cover actually is a partition into K22s if it's possible. And in that case, the order is going to equal the order of the partition is going to equal the number of edges. So you can still just ask the question, you know, what's the minimum cover? And then say, what's the order of the minimum cover? And is that order equal to the number of edges? If the answer is yes, the problem's satisfiable. If the answer is no, it's not satisfiable. Okay, an algorithm that takes advantage of that is the basis set algorithm. And the idea behind the basis set algorithm is we've got all these left sets that we're trying to represent. And what we're going to do is we're going to come up with some basis sets such that each of the left sets can be represented as some combination of these basis sets. And the way we do it is to, first of all, initialize the basis with all the singletons. So we just put in, you know, word 1 through word n as a history pair that licenses nothing. And then we actually go and we take the left sets and we initialize with the left sets. And the interesting thing here is we don't use all the left sets, but only the left sets that are below a certain size, so that when we do the following step in this algorithm, there's actually some factorization that happens. Because the following step is to compute a cover of each of the left sets in terms of these basis sets here. And then we add the variant Pij. We add Pij to the variant set associated with a word set whenever the word set is used to cover Pij's left set. I hope that made sense. It just means that, look, if we've got a set of words that licenses a variant, and we have a basis set that's a subset of that, then that subset also licenses the same variant, and so we can add that variant into the variant set that's associated with the subset that we've got. We then remove any history pairs that don't have too many entries on the right-hand side over here in the variant set, go back to step 2, repeat it, and output the cover. And here's that one in its full representation. For the interest of time, I'm not going to go over an example of running through the basis set algorithm, but it's you can just work through examples if you want. Okay, so summary of the graph building process that we developed. If we're dealing with just a unigram graph, we factor the context constraints using either the basis set algorithm or this Cartesian intersection heuristic, emit an arc decomposed graph, and then optionally determinize and minimize it using classical determinization and minimization algorithms. If we have a higher order n-gram language model that we're working with, it turns out that it's easy to take the higher order portions of the graph and just sort of graft them on to the unigram portion of the graph. There's no sort of problem. So the reason for that is if you're using left context and you've got an n-gram state like the dog ran, and you're considering a successor, you know that the last word was ran. And so there's no ambiguity in how the successor is going to be realized. And this whole business was because we have ambiguity, because if you just have a unigram portion, you don't know what the previous word was. Okay, so experimental results. There's a baseline system that uses word internal acoustic context, so it doesn't look at all across word boundaries. And we're considering 5 phones on the left of 5 phones to the left of the current phone, 5 phones to the right of the current phone. We have an 11 phone total in the context window, and that's what we're going to use. The contrast is with a long span left context acoustic model, which is the same as above, but when you compute the context window, you can actually cross word boundaries and consider words in the preceding word. I'm not sure I have performance numbers here. I got rid of a bunch of stuff to shorten up the talk. But if it's not elsewhere, the left context graph actually is a 2% performance gain over the word internal graph. So you actually get a performance gain by using this left context.
Question.
Mm-hmm.
When you look at the left context in the cross-word mode, will you cross 2 word boundaries?
No, only 1 word.
So you stop.
It would get even worse if you cross 2.
That's why you can graph the diagram on top of the...
Right.
So long span means 1 word.
1 whole word up
One
to
whole
up to 5 phones, right? That is.
Anti-disestablishmentarianism would be a little would be not.
No, the span is only 5 phones.
That word you just said, that actually is, that's just 1 word, you know.
Yeah.
Yeah.
It's
So
not with the preceding word.
right. But I mean,
It's only 5 phones. Yeah, Jason.
but recall that the whole casting of these algorithms. I hope I don't give you more than you asked for, but the whole casting is in terms of the fact that you can represent. See, all that enters into these algorithms is history pairs that looks like this, that say this variant is licensed by these preceding words, and that has nothing to do with how many phones. So even though the particular experimental results are looking at 5 phones, or some fixed number of phones, the definition of the algorithms doesn't have anything to do with phones. It's just these predecessor words license these variants. Yeah.
So when you say 5 phones, does it mean at most 5 phones?
5 phones, at most 5 phones. You'll stop earlier if you hit a word boundary. The language model, we had in this case, I think it was a 17,500 word vocabulary. There were 19,000 different pronunciation variants, tomato type thing. 17,000 unigrams, 388,000 bigrams, 300-some thousand trigrams.
Let me clarify one more thing. So when you said words, you really meant pronunciation variants, right? Because
Yes.
to the left, you really mean what phones are to the left.
Right.
So even though your vocabulary was whatever, 17,000, the number of words is really 19,000.
Exactly right. I didn't go into it because it's a potential complexity. Okay, so the Cartesian intersection heuristic versus the basis set algorithm. If you just write down the unigram graph in the sort of the brute force way, there's not too many vertices in the graph, but there's a huge number of edges. If you factor this graph, if you partition the graph to get a factorization, you vastly reduce the number of edges. There's a couple of orders of magnitude almost in there. But you were right. You're better off using covers instead of partitions. It's more general, and why not add some extra arcs or some redundant connections if you need to. And the basis set decomposition, there's a slight increase in the number of vertices, but it reduces the number of edges by almost a factor of 3 there. So we get more than 2 orders magnitude reduction in the number of edges. It's really a dramatic thing. If you look at the full trigram, what do we have? When we have word internal acoustic context, don't do any minimization at all. We just write out the graph in that simple way that I showed on slide 3 or 4, or whatever it was. 1.5 million arcs and 3.7 million arcs. If we apply classical state level determinization and minimization to it, guess what? State minimization can be a misnomer here. Look at that. The number of states actually got bigger, and the number of arcs actually got bigger. Why is that? It's because minimization applies to a determinized graph, and determinization can exponentially increase the size of a graph. So even though you've got a minimized graph, you better be careful. If we don't do any kind of factorization or minimization to the left context graph, again, we've got like 300 plus million arcs. And the program couldn't write it down, so I couldn't figure out how many states there were exactly. If you do the arc minimization or the arc factorization, you end up with 9.4 million states. This 300 drops to 21. And then if you apply the classical state determinization and minimization, in this case, you do get a benefit. I guess we were kind of sloppy in writing out the graph. And the interesting thing here is that even when you have this full word of left context, the final size of the graph is basically the same as when you don't have any left crossword context at all. You go from 4.2 to 4.8, and this 1.8 to 2 is basically the same. If you want more detail on any of these, there's a conference paper and a journal paper here you can look up. I think this is sort of an interesting problem, and it's got some interesting related problems. One of these is to find the maximally compact representation of a bigram language model. So a fully enumerated bigram language model is, again, one of these bipartite graphs that's got all kinds of stuff in it. In fact, you've got a connection from every word to every other word, and you'd like to shrink that. Well, a simple way of shrinking it is just to put one state in the middle, and then you can go from every word on this side to that middle state, and then from every word in this state to the other words. Why not do that? Well, the problem is that in the bigram case, now all of a sudden you have costs on the arcs. And it's not just a question of going from word A to word B. It's a question of going from word A to word B with a fixed cost. And so if you take those n squared edges and replace it with 2n edges by putting the null state in there, you're never going to get the costs to approximate the cost that you had in the first place, which makes it even a more interesting problem, because basically the question that you want to ask is, what's the minimum number of arcs that I can use to represent this graph such that no cost from A to B differs by more than X% from the cost in the original graph? You want to formulate questions like that and then try to answer those. The other sort of related interesting question is the general question of trading non-determinism for size. AT&T has developed a set of techniques for minimizing graphs. These operate only on determinized graphs. And that whole framework is done sort of, that the whole process is done in the concept, in the framework of having determinized graphs. But when you run Viterbi, Viterbi doesn't care about whether a graph is determinized or not. All Viterbi knows is states and arcs, and it takes maxes over incoming arcs. It doesn't know anything about is this graph deterministic or not. And so the question is, can you take a graph and sprinkle some extra nodes in there in strategic places, which is going to increase the number of arcs in the graph. Increase the number of states in the graph because you're adding extra states. So it's not state minimization. You're increasing the number of states. You're sprinkling extra states in there. And you're adding non-determinism because you're going to label these things with epsilons, and epsilons are not good for determinization. But reduce the number of arcs by quite a bit. Can you do that? So I think that's an interesting general question. And so just to conclude, we've developed a method for making static decoding graphs that use a full word of left context, identified an interesting NP-complete optimization problem that we've got to solve in order to actually make that process practical, presented effective heuristics for solving that NP-complete optimization problem. And when you do all this stuff, it turns out that you can get some very speedy and effective decoding results. Thank you.
Can you go back to the slide where you talked about the context that you actually used the long and short span? Yeah, there we go. Okay. So your strategy here, this is like going way back to the assumptions underlying the talk. Your basic strategy was to multiply out the entire set of previous word following word pairs, or preceding word following variant pairs, and then try to merge them back together. Right.
Yeah.
So there's another way of going about things, which is to start out with a no context model. So in effect, a unigram model where the variant, the word number 2 doesn't depend at all on word number 1.
Okay.
And then start splitting. And I might be inclined to try it that way, rather than trying to break Humpty Dumpty up and then put them back together again. Because it seems like there's a natural way to do it. Namely, you start with a simple model, and then you compose it with transducers that modify the word number 2 based on the ending, for example, of word number 1, which is what you're looking at here. So how would that compare?
I haven't done it. I don't know. I mean, the devil is in the details in these things, and I think you just have to, first do it to make sure that you can actually dot all the I's and cross all the T's, and the whole thing does what you think it's going to do, and then you'll know if it's better.
But wasn't there something like this? Maybe I thought it was also an idea. Maybe it was that when you looked at doing the crossword expansion, when you went down the decision tree one step at a time.
Right.
That seems to have a similar flavor to it, doesn't it? Instead of looking at one phone, you just look at one question about.
Right. So the difference here, well, there's two differences. The first difference is this came first, and this is what caused that other work to happen in the first place. But the second difference is that this isn't tied to a decision tree. Because again, recall that the constraints were presented in terms of this set of words licenses these pronunciations. So the whole thing is cast in terms of words, and that's different.
This issue of partition versus covers, if you have multiple redundant parts and you're pruning, then wouldn't it matter how much redundancy you have in the paths? Because if you have too many redundant paths in your beam, then you might be losing other paths.
That's an interesting point. I haven't noticed any difference in decoding speed between the graphs that are built one way and the graphs that are built the other way. But that's interesting. You're right. I mean, there's a reason to believe that something like that would happen.
Could you say something actually about the way that the weights are chosen during the cover algorithm? You gave a Boolean version of this instead of a weighted version for purposes of simplicity, but obviously when you do this in practice.
Oh no, there's no weights involved. That's one of the nice things about the problem.
Oh, I see. All right. Okay.
You can either, if you look at one of these.
I'm sorry. Every word only picks one variant for the following. Right. There's
Right.
no weights involved. Okay.
Okay, I was. Yeah, it's like this. If you finish a word, you go and you pick one other variant. So it's basically a 0-1 type thing that you're doing. There's no. In fact, you can represent this whole thing as 0-1 matrix factorization, where you've got basically you start with a big adjacency matrix. It's just filled with zeros and ones, and it's the number of words in the vocabulary by the number of words in the vocabulary, and then you factor that 0-1 matrix into the product of a tall skinny matrix and a short fat matrix, right? Anything else?